Lesson 10-1, Factors and Greatest Common Factors. And in this lesson, you learn to find prime factorization of integers and to find the greatest common factor. For sets of monomials, why is this important? Because you can use factors to solve problems involving packaging and gardening. Now, we already started this in 6th grade and also in 7th grade. And in Algebra 1, we are going to take this one step further. So let's take a look at this geometry application. Suppose you were asked to, to grid paper to draw all of the possible rectangles with whole numbers dimensions that have areas of 12 units each. Okay, the figure at the right shows one possible drawing. So you want to find all possible rectangles with whole numbers that have the areas of 12 units each. So these are all 12 units, okay, of rectangles, because if you count the squares, they're 12. Okay, so rectangles A and B right here. Okay, both are 3 by 4. Okay, therefore it can be considered the same. Likewise, rectangles C and D. Okay, and E, F, E are considered the same because they have the same dimensions. Recall that when two or more numbers are multiplied to form a product, each number is a factor of that product. So in the example above, 12 is expressed as a product of different pairs of whole numbers. So with the example right here, you notice that the factors of 12 can be 3 times 4, okay, or 4 times 3. It can be 2 times 6 or 2 times 6. So 2 times 6 times 6 times 2. This is what you get in rectangles C and D. And rectangles E and F will have dimensions 12 times 1 and 1 times 12. So the whole numbers 1, 2, 3, 4, 6, 12 are factors of 12. Okay, very basic. Let's take a look at example number 1. Find the factors of 72. And finding the factors of 72, from what we learned in 6th grade and 7th grade, we want to list all the pairs of factors whose product is 72. And we have 1 times 72, 2 times 36, 3 times 24, 4 times 18, 6 times 12, and 8 times 9. So therefore, the factors of 72 in increasing order are 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. We simply list all of them in increasing order. So 1, 2, 3, 4, 6, okay? And then we move on to the next order after that will be 8 and 9 right here, and then 12, 18, 24, 36, and 72. Okay, and let's recall what prime and composite numbers are. Some whole numbers have exactly 2 factors, the number itself and 1. These numbers are called prime numbers. Again, definition of a prime number. Okay, a prime number is any whole number which has exactly 2 factors, 1 and itself. Okay, and remember, prime numbers can never be negative. Prime numbers are always positive. So whole numbers that have more than 2 factors are called composite numbers. Okay, so if it's not prime, it's composite, except for 2 numbers, and those 2 numbers are 0 and 1. So 0 and 1 are neither prime nor composite because 0 has an infinite number of factors and 1 has only one factor itself. So let's define prime and composite numbers. A prime number is a whole number greater than 1 whose only factors are 1 itself. A composite number is any whole number greater than 1 that is not prime. Okay? So moving on. The number 6 is a factor of 12, but not a prime factor of 12, since 6 is not a prime number. So when a whole number is expressed as a product of factors that are all prime numbers, the expression is called the prime factorization of the number. Thus, the prime factorization of 12 is 2 times 2 times 3, or 2 squared times 3. Okay, remember we used a factor tree for this one. So if you want to find the prime factors of 12, you simply get 2 factors of 12, in this case 3 and 4. And we know that 3 is prime, so we circle 3 and continue factoring 4 since 4 is not prime yet. And the 2 factors are 2 and 2. And all the circled numbers are all prime, so it's 2 times 2 times 3, or 2 squared times 3. Okay, so the prime factorization of every number is unique except for the order in which the factors are written. So for example, 2 times 3 times 2 is also the prime factorization of 12, but it is the same as 2 times 2 times 3. So this property of numbers is called the unique factorization theorem, where any number will have a unique set of prime factors. Okay, let's take a look at example number 2. Find the prime factorization of 140, method 1. Okay, we get 2 times 70. The least prime factor of 140 is 2. And then we get now 2 times 2 times 35, because we multiplied 2 times 35 will give you 70. And then from there we get 2 times 2 times 5 times 7, now because we simply bring that down, bring that down, bring that 2 down, and 35 is a product of 5 times 7. And if you notice, 5 and 7 are also prime. And therefore, all the factors in the last row are prime. That's a prime factorization of 140 is 2 times 2 times 5, or 2 squared times 5 times 7. Okay? Or we can use a factor tree like what we did in 6th grade and 7th grade. And if we use a factor tree, we simply first get 2 factors of 140, doesn't matter which one. And let's get 10 and 14, doesn't matter really. So 10 and 14 will give you 140, and we know that 10 is not prime, so we continue factoring 10. 2 factors of 10 are 2 and 5. Those are both prime, so we both circle those numbers. 14 is not prime, continue factoring. This is 2 times 7. So the prime factorization of 140 is 2 times 2 times 5 times 7, or 2 squared times 5 times 7. Okay? So a negative integer is factored completely when it expresses a product of -1 and prime numbers. So when you want to factor -150 completely, first you need to factor out -1. Okay, and then we can factor it completely. Okay, so -$150. Sorry, -150 factored completely. We need to factor out -1 first. So this is -1 times 150. It'll give you -1 times 2 times 75. Find the prime factors of 150. Okay. And then we find the factors of 75. 3 times 25. And eventually find the factors of 25. So you now have -1 times 2 times 3 times 5 squared. Okay? And that's how you factor -150 completely. If you notice, it did not say find the prime factorization of -150. The reason for that is what I mentioned in the definition of a prime number. Okay, a negative number cannot have, or all prime numbers are positive, and that's the reason why you cannot say find the prime factorization of -150, because -150 by itself is not will not apply to the prime factorization rule. So let's take a look at example number 4. Factor 45x cubed y squared. Again, 45x cubed y squared. Okay, find the factors of 45, which will be 3 times 15. And we simply expand x cubed to be x times x times x, and y squared to be y times y. And then we factor 15. 3 times 3 times 5 times x times x times y times y. Okay, and this is now the factor of completely factoring 45x cubed y squared. Okay, before we go to the definition of the greatest common factor, Let's take a look at this one. Two or more numbers may have some common factors. Consider the numbers 84 and 70, for example. So the factors of 84 are 1, 2, all the way to 84. Factors of 70 are 1, 2, all the way to 70. And if you notice, okay, there are some factors appear on both lists. The greatest of these numbers is 14, right here. So in this case, okay, even though there are other factors, 2 is a common factor, 1 is a common factor, okay, 7 is also a common factor, but the greatest common factor, okay, of 84 and 70 is 14. Okay, so definition of the greatest common factor, which is the greatest common factor of two or more integers, is the greatest number that is a factor of all of the integers. And like what we learned, we can use the prime factorization to be able to find the GCF of two numbers. Okay. So again, like I told you, there's an easier way to find the GCF of numbers without having to find all their factors. The reason why it's easier, because once you start having numbers that are huge, like for example, find the GCF of 1324 and 465, looking for factors would be a very difficult task. Okay, so look at the prime factorization of the numbers and multiply all the prime factors that they have in common. If there are no prime factors, the GCF is 1. And again, a lot of these things you forget to look at. So if there are no common prime factors, their GCF is equal to 1. So if you look at the GCF, if you want to find the GCF of 84 and 70, we get the prime factorization of 84, which is 2 times 2 times 3 times 7, and 70 is 2 times 5 times 7. So if you list them, okay, horizontally, so you have 84 is equal to 2 times 2 times 3 times 7, and you have 70 is equal to 2 times 5 times 7. And if you notice, 2 is common to both, and then 7 is also common to both. And to be able to find the GCF, you simply bring these two down, and you end up with 14. Okay? And there's a reason why in 84 and 70, using prime factorization, this would be an easy way to find the GCF. Okay, let's take a look at the GCF of three numbers now, 54, 63, and 180. Okay, so the prime factors of 54 are 2 times 2. Sorry, not 2 times 2, it's 2 times 3. Okay, times 3 times 3. Prime factors of 63 are 3 times 3 times 7, and 180 prime factors are 2 times 2 times 3 times 3 times 5. And we simply circle the common factors of each row. So the 3 is circled because 3 is common to, oopsie, let's do that one. Let's redo that one. Okay, so we circle the 3, common to all 3, and another 3 right here, common to all 3. And we simply bring them down once. Okay, so bring this 3 down once, bring that 3 down once, and you multiply them. So the GCF of 54, 63, and 180 is 9. Okay, let's take a look at example number 6. So in example number 6, a bakery packages its fat-free cookies in 2 sizes of boxes. One box contains 18 cookies and the other contains 24 cookies. To keep the cookies fresh, bakery plans to wrap a smaller number of cookies in a cellophane before they are placed in the boxes. To save money, the bakery wants to use the same size cellophane packages for each box and to place the greatest possible number of cookies in each cellophane package. So again, this is a GCF problem. So in letter A, how many cookies should the bakery place in each cellophane package? And letter B, how many cellophane packages will go in each size of box? So we find first the GCF of 18 and 24. Okay, so 18, the prime factors of 18 are 2 times 3 times 3. Prime factors of 24 are 2 times 2 times 2 times 3. And then we circle our common factors. This is common, and that is common. Bring them down once. Okay, bring this 2 down once, 2, and that 3 down once, 3, 2 times 3. Okay, the bakery should put in 6 cookies in each cellophane package. Okay, letter B, so how many cellophane packages will go in each size of box? So we basically get this our GCF, which is 6, okay, and simply ask ourselves, what did we multiply 6 to get to 18? What did we multiply 6 to get to 24? So the 18 box cookies will contain 3 cellophane packages, and if you notice, okay, that is the number that has not been circled, the number 3 right there. Okay, and the 24 cookies will contain 4 cellophane packages. Again, those are the numbers that have not been circled. Okay, so we either get 18 divided by 6, 26 divided by 6, or simply look at our prime factorization and see what numbers have not been circled. That would be the answer to letter B. And finally, last example, find the GCF of 12a squared b and 90a squared b squared c. Okay, now we're using monomials. And then first we get the prime factors of 12, which are again 2 times 2 times 3 times a times b. Sorry, completely factoring 12a squared b would be 2 times 2 times 3 times a times b. And completely factoring 90, a squared b squared c would be 2 times 3 times 3 times 5 times a times b times c. And we circle our common factors. We circle that. We circle that. We circle this a. We circle that a. And we circle that b. And we bring them down once. Okay. So if I bring them down once, I don't want to bring it down here because there's a sentence going to appear here. So if I bring them down once, it's going to be 2 times 3 times a times b. Or that would be 6a squared b. Okay, and that is a GCF of those two expressions. And the secret word for this particular lesson would be nets. The secret word would be nets. Thank you for watching.